In this section of the course, we're going to be running through a practical example, taking one dataset and running through all the steps that we've covered in this course in a real-life business setting. Let's set the scene. So imagine you're working for a social media company and the company is concerned with the growing amount of fake news circulating on its platform. They've assigned you as a data scientist to investigate how fake news can be recognized and create a method of identifying it. Let's work through this problem together, first by exploring and cleaning the data, and then working to classify fake versus factual news stories. We'll also create some plots of our outputs and discuss how we will communicate our findings to stakeholders. So the first thing we're going to want to do is import the necessary packages. So you'll recognize these from our previous lessons. We're using the pandas package for data manipulation, matplotlib and seaborn for plotting, spaCy, ARI, NLTK, gensim and sklearn for all the different types of analysis that we want to do. We're also going to set some plot options to get started. So we're going to be setting the figure size as 12:8 to make sure all our charts are printed in a nice size, and we'll also specify a default plot color to use. So now that we've got all that set up, let's import our data. So we're going to create data and use pd.readcsv and read in fake news data.csv. Let's have a look at what this data looks like with data.head. We've got the title of a news article, the text contained within the news article, the publication date, and then a tag of whether this is fake news or factual news. We can then use data.info to get some more information about this dataset. So you can see we've got 198 entries, so 198 rows in our data, and we haven't got any null values, so we don't need to take care of this. Before we move on to any kind of comparison between the fake and factual news articles in this dataset, we need to make sure we've got an appropriate number of rows in each group. So let's plot this out and see what it would look like. We want to take our fake or factual column from our data frame and then use value counts and plot. Within the plot function, we specify we want this to be a bar chart, and for the color, we can include the default plot color. We'll also include a title, so the count of article classification. So we can see now from this chart that we've got equal numbers of fake and factual news articles, which is perfect to go forward in our analysis. If we did have significantly different numbers of rows in each group, we would need to take some steps to make this a balanced data set. In our case, we're fine to continue with our analysis. So let's go forward to our next lesson and start exploring this data a little bit. So before we get started with any text pre-processing, let's explore our dataset a little bit more. We'll start with some POS tagging. So the first thing we're going to want to do is initialize our spaCy model. So we'll do this with NLP equals spaCy.load and then reference the model we want to use. Because one of our tasks is to determine the differences between fake and factual news, we want to split out the dataset into fake news and factual news, and then we can compare the POS tags that occur between each of the different datasets. We'll create our fake news dataset, just taking our data frame and splitting it out where the column fake or factual equals fake news. We'll then do the same for fact news and take our data frame and filter it to where fake or factual equals factual news. From this, we can then create our two separate spaCy documents. So first, we'll take our fake dataset and create fake spaCy docs. Because we're working over a data frame, we'll want to use nlp.pipe over our fake news text column, and then make this a list. We'll then do the same for the factual news, so fact spaCy docs equals list, nlp.pipe over our fact news text dataset. We then want to create a function to extract the tags for each of the documents in our data, so each of the rows in our data frame. So we create our function extract token tags that takes the argument doc spacey.tokens.doc.doc. It will then return text, the ent type, and the POS tags for each item in the document. You'll notice here we're not only extracting the POS tags, but the ent type for named entity recognition, which we'll come onto later. So now let's get stuck in and start tagging our dataset. First, let's take the fake dataset. We'll create an empty list called fake tags df. And then we'll specify the column names we want to use. So we've got token, NER tag for the named entities, and POS tag. We then want to iterate through each of the documents, so each of the rows in our data frame, and pull out the relevant tags. So we'll create our for loop. For ix doc in enumerate fake spacey docs, we'll take the tags by using our extract token tags function that we created earlier, and the argument we provide is the doc. We then convert these tags into a data frame and give the column names as the columns we specified earlier. We'll then append these tags onto our fake tags df. Once we've run through each of the documents and we've populated our fake tags df, we'll then use pd concat to get it into the right function and assign this back to fake tags df. So we'll do the exact same thing for our factual dataset, so we'll create fact tags df, and then we can just copy the code down and switch it out for the relevant dataset that we need. Let's see what this looks like. We'll take fake tags df.head. And we can see here this dataset has been broken out into the individual tokens, named entities have been pulled out where appropriate, and each token has been given its relevant POS tag. If you remember from our earlier lesson, the next thing we'll want to do is take a token frequency count. So we'll create our POS counts fake, and then fake tags df.group by, and we'll group by the token column and the POS tag column. We'll then take the size of this group and reset our index. We'll then use the name argument to name the index as counts. Next is .sort values, and we want to sort by the counts, and ascending equals false. Once we've done that, we can take POS counts fake.head, and we'll specify we want 10 rows to be returned. So essentially what we're being shown here is the most frequently occurring tokens, their associated POS tag, and the number of times this token occurs within our dataset. So because we haven't cleaned our dataset yet, you can see that this is just punctuation and stop words. This isn't super interesting, obviously, from an insights point of view, but it definitely helps when you come to removing your stop words. You can reference this list and make sure that any kind of really frequently occurring words that you don't want in your dataset are properly included within the stop words. We'll then do the exact same thing for our factual dataset, so we can copy this code across and switch out the datasets from the fake dataset to the factual dataset. We'll run this, and again you can see the most frequently occurring tokens. Again, it's just punctuation and stop words, but it's really good to be able to see this, to visualize it, get an idea of what kind of words you want to remove later on in the process. The next thing we want to look at is the frequencies of individual POS tags, so how many nouns occur, how many adjectives occur, things like this. It'll be interesting to compare this between the fake and factual dataset to see if different types of tags are coming up more frequently. So to do this, we take our POS counts fake that we just created and use the group by again. Here we're just grouping by the POS tag and then we're taking the token. We'll then count these tokens and sort the values. Again specifying ascending equals false to get the most frequent first. So we can see here nouns have the most unique values, followed by verbs and proper nouns. Let's compare this now against our factual dataset. Again, we'll just copy that code across and switch out the appropriate dataset. And when we compare this, we see that the two datasets do kind of follow a similar pattern, with nouns, verbs, and proper nouns being the most frequently occurring tags. You could then ask yourself, okay, well, if this is similar, are the specific nouns that are being used also similar, or do they vary quite a lot between the different datasets? Let's investigate this by doing a deeper dive into the nouns used by each of the datasets. So from our POS counts fake, we want to filter this to where POS counts fake.pos tags equals noun. So we're essentially just taking our dataset, filtering it to where the POS tag equals noun, and then we're giving the top 15 results. These will give us the top 15 nouns used in our fake news dataset. So we've got the top 15 printed out now, and we can see that the most popular nouns are words like people, president, women, time, year, etc. Let's see if this is the same for our factual news dataset. Okay, so we can see that even though nouns are really common in both datasets, the words they use do differ quite a lot, or at least have different places in the frequency of how they're used. So we can see government is the top noun in our factual dataset, but in our fake news dataset, this is way lower. We also have words included in the factual dataset such as bill, administration, election. Election does occur in the fake news dataset, but again, it's much lower down. So it's interesting to compare these two lists and see, okay, even if the frequencies of POS tags and how often they occur is quite similar, the different words that fall under each category can differ quite a lot. If you want to, feel free to pause this video now and take a look through some different POS tags and see how the words vary between each of the two datasets. And if you're ready to move on, let's move to our next lesson where we look at the named entities between these two groups. So now we're going to be looking at the named entities in this dataset. And you'll remember from our earlier lessons that it is better to do this before you do any kind of text pre-processing. So that's why we're doing it now, to give our models the best chance of pulling out those interesting named entities before we go in and do any kind of pre-processing and cleaning of the data. Because we already pulled out the named entity tags in our last lesson when we did the POS tagging, we don't have to do that step again. We can just jump straight in and start looking at what's been pulled out. So we want to start by pulling out the top entities in our fake news dataset. So we'll start by creating our top entities fake, and this is going to be our fake dataset filtered to where the NER tag column is not blank. So this means going through and taking any token that has been recognized to have a named entity in there. We then want to group by the token column and the NER tag column, take the size, reset the index, name it counts, and then sort our values by these counts in descending order. We then want to do the same thing for our factual data, so we'll copy this code over and just swap out the correct data sets. So we're swapping our top entities fake for top entities fact, and our fake tags df for our fact tags df. I then want to create some nice plots of the named entities that have been pulled out so that we can use this in presentations or take it to stakeholders. So the first thing we want to do is create a colour palette to make sure that both plots are in the same colours for the different named entity tags. So for example, if we've got different people being pulled out of the different data sets, we want to make sure that's going to be represented by the same colour in both of our plots, so it looks nice and it's easy to understand. We can then go on to use the Seaborn package to create some really nice looking plots. So we're going to start with sns.barplot. We specify our x and y, so our x is going to be the counts and the y is going to be the token. We then specify the hue, which is the colour to use for each bar. So here we're wanting to colour by the NER tag, and the palette we want to use is our NER palette that we created a step earlier. We then specify our dataset, so we're taking our top entities fake, and we just want the top 10 entities for this plot. We then change it to a horizontal bar chart using Orient equals H, and we specify Dodge equals false to get the bars in the right format. We then also set our title to the most common entities in fake news. We can see here the most common named entities that have been pulled out are people, and this is really clearly demonstrated by the colours we chose to use. I wonder if in the factual news dataset, similar names are coming up just as often. So let's copy this code over and have a look at what this chart would look like when we run it over our factual news dataset. So you can see here people's names are much less common. In fact, Trump is the only name that occurs once we look at the top 10 entities pulled out of our factual news dataset. Here, organisations and place names seem to be much more common, and there's less of a focus on people. So if you remember when we set up this problem, one of the aims is to investigate how fake news can be recognised. So you can potentially take from this that more names might be used in fake datasets and less so in factual news. This is something you could then do a deeper dive in and explore this more and really get into the data to answer that question for your stakeholders. Let's jump into our text pre-processing and start cleaning up this data for some more advanced analysis. So far, we've loaded in our dataset and explored it a little using parts of speech tagging and named entity recognition. Now we're ready to start pre-processing our text data. We've covered this a few times now, so I'm hoping you'll be an expert in cleaning up this data. First, let's run data.head just to refresh our memories on what this dataset looks like. So you can see we've got the title column, the text column, the date, and the fake or factual tags. We want to clean up just our text column. You'll notice some rows in the text data have a location tag at the start of the text. So for example, in the bottom two rows, you'll see Washington and Belfast. There's also the router's name in there, followed by a hyphen. We want to clean this up and remove it because it feels like it might impact our analysis a little bit. So how can we do this? Well, we can do it using regular expressions. The aim of this regular expression we're going to create is to look for this hyphen and remove everything before that first hyphen. So we want to create our new column, text clean, that's going to contain all of our cleaned up text. We'll then use data.apply to apply our RE sub function over the rows in our dataset. So we'll specify lambda x and then use RE sub and a regular expression. This regular expression is probably going to look a little complicated, but essentially what it does is look for the first hyphen in the text and remove the hyphen and everything before it. If you do struggle with creating a regular expression for your problem, I definitely recommend having a Google because there's usually someone who'll have the same problem and will have provided a solution for you. There's also some great regex generators online that you can use to help create the regular expression syntax you need for your problem. So we specify the regular expression syntax and we want to replace this with blank. So essentially we want to remove it from our text. We then specify we want this to run over the text column, and our axis equals 1. So if we go back and run our data.head again, we can see that our text clean column has been added, and those location tags have been removed. Our next step, as I'm sure you'll remember, is converting our text into lowercase. So we take our text clean column, and then we just apply .str.lower. We then want to remove our punctuation, so this is the same code as we used before for our regular expression, except we're just switching out the syntax. This syntax will be the one you recognise that we've used to remove punctuation in our other lessons. It's basically looking for anything that isn't a word or a space and just removing it. So again, we'll run data.head and we can see that our text clean column has been nicely converted into lowercase for us. We'll then move on to removing our stop words. So we'll specify the stop words we want to use, we'll create en stop words, this equals stop words.words, and we'll specify the language of the stop words that we want, so English. We'll then print these stop words out and have a look at what's in there. So when we did our POS tagging, you'll remember I said it was important to compare those frequently occurring tokens against our stop words list. So here you can see we had the really common tokens that were mostly stop words, so the, of, a, and. So it's really important to go back and sync that up with your stop words list and make sure that all those really commonly occurring words that you can remove are in that stop words list to be removed. So I know that these tokens we want to remove are in the stop words list, so we can go forward and just straight up remove them. Again, let's check our pre-processing by rerunning our data.head. So when we look at our text clean column and compare it to our text column, we can see that stop words have been removed. Now let's jump into tokenizing this text. This will go through each of the rows in our dataset, take the text from text clean and convert it into our word tokens. And our final step in pre-processing is going to be lemmatizing. We're going to be using lemmatizing instead of stemming because I want to use this more intelligent method to keep a lot of the context and meaning of the words where possible. Our dataset isn't too large, so it shouldn't take too long to run and won't cause too much of an issue later down the line. We've specified our lemmatizer as our WordNet lemmatizer, and then we use lemmatizer.lemmatize, and in the brackets specify our tokens for token in tokens. Let's check this last bit of pre-processing. And great, you can see that text clean has been tokenized and lemmatized successfully. Now that we've cleaned that up, let's see what our most common n-grams look like after we've done this pre-processing. So we'll create a list of our clean tokens and then go on to look at the unigrams. So we create unigrams and then we want to create a PD series and we'll use nltk.ngrams over our tokens clean. We specify the value of n as 1 because we're just interested in unigrams. We then want to take the value counts. And we can print this out up to the top 10 to get our top 10 most frequently occurring unigrams. So we can see this is much more interesting after we've done our pre-processing. It's not just stop words anymore that are coming up as our most frequent tokens. We've got much more interesting words coming out here. So let's turn this into a plot so we can put it into any presentations or discussions we're doing with non-technical people. We'll use the Seaborn package, so we'll use sns.barplot. we'll specify our X to be unigrams.values up to the top 10, and our Y is the unigrams.index, again just up to the top 10. We want to specify the orientation as horizontal, so we use H. And for our palette, we're just going to be using the default plot color we specified at the start of our notebook. Of course, we also want to add a title, so we'll name this chart Most Common Unigrams After Pre-Processing. And once we've run that, it's given us a nice chart we can use of the most common unigrams in our dataset. Let's see if analysing the bigrams give us similarly interesting results. So we'll copy this code over and just switch it out to bigrams, making sure to remember to change the value of n from 1 to 2. So here again you can see we've got some really interesting bigrams coming out, such as Donald Trump, the United States, White House, etc. So now that we've cleaned up our dataset and got it all in a nice format, let's move forward with some additional analysis. So in this lesson, we're going to be trying to answer the question, does sentiment differ between the different news types? So for example, does factual news have a more positive or more negative skewed sentiment as compared to the fake news dataset? Let's work through some sentiment analysis and try to answer this question. We're going to be using the Vader sentiment calculation to get our sentiment analysis. So we'll start by initializing the sentiment analyzer. So we create Vader sentiment, and this equals our sentiment intensity analyzer. We then want to create a column for our sentiment score. So within our data frame, we create the column Vader sentiment score. We then take the data.text column, so we're going to be using the raw data to calculate this. We apply the lambda function and take our Vader sentiment polarity score from our text. We then want to just take the compound from this output. If we now print out the first few rows of our dataset, we can see our Vader sentiment score with the relevant sentiment score for each of our documents. We want to classify this into positive, negative, and neutral sentiment. So first we want to specify the bins. So we create our bins from -1 to -0.1. This is going to be our negative classification. From -0.1 to positive 0.1, this is going to be our neutral sentiment. And anything from 0.0.1 above up to 1 is going to be our positive sentiment. We then create our Vader sentiment label column and use the pdcut function. This function takes our Vader sentiment score column, chops it up by the different bins, and gives them the labels that we specified in our names above. Again, let's just run data.head to check our working. Perfect, so you can see here all the sentiment scores that are less than -0.1 have been classified as negative, and there's a few positives in there as well that have been correctly categorized. Let's now see if we can use this to answer the question of whether sentiment differs between the two different types of news articles we have. We want to create a bar chart of the different labels in each of the data. We'll first start by just looking overall how many positive, negative, and neutral sentiments we have across the whole dataset. So we'll use data Vader sentiment label .value counts .plot .bar, and the color will be our default plot color. So from looking at this chart, you can see that overall we've got a few more news articles with a positive sentiment as opposed to a negative sentiment. And we've just got a few neutrals in there. Most of them have been classified as positive or negative. Let's now look at how this varies between the two types of news articles we have. So we want to use sns.countplot. Our X is our fake or factual column. Our hue, so our color, is our Vader sentiment label. And the color palette we're going to use is the SNS color palette HLS. We also want to set the title, so we're going to call this Sentiment by News Type. So let's look at this plot and what it tells us. When looking at the fake news, we can see there's a pretty even split between positive and negative sentiment, and a few neutrals in there, but there isn't really a massive skew to one or the other. In our factual news dataset, if you just look behind the legend, you can see that positive does skew more in this dataset. So we have a few more positive articles as opposed to negative in the factual news dataset. There's also a lot less neutrals in this. So the differences aren't drastic, so I don't think you could say at this moment that factual news skews more positive and fake news is a little bit more evenly distributed. It would require a bit more of a deep dive. One thing we could also do is try to change the method we've used of determining sentiment. So we could experiment with different rule-based models, or we could implement the pre-trained transformers that we're now comfortable in using. Now that we've had a look at our sentiment analysis, let's move on to exploring topics within this dataset. So in this lesson, we're trying to address the question of what topics appear in our fake news. We're interested to see if any particular topics come up that might help us identify a fake news article. For this, we're going to obviously be using topic modelling, and we're going to start by using latent Dirichlet allocation. The first step for us is going to be vectorizing our text. We want to convert our text into numbers that can be fed into the LDA algorithm. So let's start by creating our fake news text, which is just going to be our dataset filtered to where fake or factual equals fake news, and then we're just taking our text clean column and resetting our index. This is just going to leave us with the cleaned up text from any article that's been classified as fake news. We then want to create our dictionary. So to do this, we use corpora.dictionary and then reference our fake news text. And finally, we want to create our bag of words. So we create our document term fake, and then from dictionary fake, we take doc to be of words over our text for each of our texts in fake news text. So we're going to jump straight in to generating coherence scores to determine the optimal number of topics. So we create an empty list for our coherence values, and we create an empty list for our models. We also specify the minimum topics we want to test, which we'll set at 2, and the maximum topics we want to test, which we'll set at 11. Let's now create a for loop to run over each of the iterations of this model. So for num topics I, in the range from the minimum topics to the maximum topics plus 1, so from 2 to 12. We then create our LDA model, feeding it our doc term fake. Our number of topics will be specified to the num topics I for each of the iterations of our for loop, and ID to word is our dictionary fake. We then want to take this model and append it to our model list. From this, we can then create a coherence model for the model we're using in this for loop. So we use coherence model, model equals model, text equals fake news text, dictionary equals dictionary fake, and coherence is C_V. We then append coherence model get coherence to our coherence values. So what this loop will leave us with is a list of all our models in models list and a list of the coherence values put into our coherence values list. Let's now plot these coherence values to see what they look like for each of the iterations of our model using a different number of topics. We're going to use plt.plot And we're going to be plotting the range from our minimum topics to our maximum topics plus 1 against our coherence values. We add a label to our x-axis for the number of topics. We use plt.ylabel for our y-label axis, which will be the coherence score. And we add a legend for our coherence values and specify the location. So we can see the coherence scores are highest when the number of topics was set to either 2, 7, or 11. For our example, we feel like 2 topics might not give us enough interest, whereas 11 topics is going to be too difficult to explain to different stakeholders and get an understanding of what those topics are around. So let's create our final LDA model with 7 topics. We specify the number of topics that we've chosen to be 7. We then create our LDA model. We use gensim.models.lda model as we used before and reference our .term fake, our dictionary, and our number of topics we want to use. We can then use LDA model.printTopics to print out the words that occur with each topic. We specify the number of words as 10. We want to see the 10 most common words for each of the topics. When we look through these topics, we can see that there is quite a lot of overlap. So, for example, the word Trump is a really frequently occurring word in all of the topics, as is the word said, and other words throughout there as well also appear in a number of different topics. In our next lesson, let's try some different techniques to pull out some more interesting topics and hopefully get some more insightful analysis. Because a lot of the topics in our last lesson came out to be really similar, let's try some different methods. The first thing we can change is using the TF-IDF vectorization of our text, as opposed to just the bag of words model. We're going to be using latent semantic analysis, as opposed to latent Dirichlet allocation, to see if that gives us different results. For this lesson, we're going to be creating a couple of different functions. The first thing we want to do is define a function to create our TF-IDF corpus. So we start by defining this function, TF-IDF corpus, and the argument it should receive is a document term matrix. The next step is to create the TF-IDF model. This takes the arguments of the corpus, which is our document term matrix, and normalize equals true. We then create our corpus TF-IDF, which is the TF-IDF doc term matrix. Our function will then return this corpus for us. We then want to create a function to get the coherence scores, so we can find the most optimal value for our number of topics. So we define the function getCoherenceScores, and the arguments it wants to receive are the corpus, the dictionary, the text, the minimum number of topics, and the maximum number of topics we want to test. We'll then create an empty list for our coherence values and an empty list for our models list. We then create our for loop, so for num topics I, in range min topics to max topics plus 1. We create our model using the LSI model, which takes the arguments corpus. The num topics will be set to the num topics I for that iteration of the for loop, and the ID to word will be our dictionary. We then append this model to our model list. The next step is to create the coherence model, which will take the argument of the model, the text, the dictionary, and the coherence, which we set to C_V. We then append the coherence module.getCoherence to our coherence values and create a plot. The plot will be plotting the number of topics against the coherence values. We also add the appropriate X label for the number of topics, the Y label for the coherence score, the legend, and we want to include PLT show to make sure our plot is printed out correctly. So now that we've defined our functions, let's create our TF-IDF representation of the text. So we create our corpus TF-IDF fake, and this equals TF-IDF corpus, which is the function we created earlier, and then we provide it with our doc term fake, which is our document term matrix. From here, we can get the coherence scores using our getCoherenceScores function. The corpus is the corpus TF-IDF fake, our dictionary will be dictionary fake, our text will be fake news text, and we'll use the same arguments as our last lesson. So our minimum number of topics will be 2, and the maximum number of topics we want to try will be 11. Now we have our coherence scores, we can see that the optimal number of topics looks like it will either be 10 or 7. Let's now create our final model. So we specify our LSA model and we use the LSI model function. We feed it the corpus TF-IDF fake, our dictionary fake, and we set the number of topics to 7. So our first topic seems to have the words Trump, Clinton, and Hillary. The second topic, boiler, ARC, room. The third topic, Flynn, immunity, Nana. And again, if you read through the topics, you can see there's a lot more differences here compared to when we ran it in the last lesson. These are much more interesting topics to discuss and dig into what these differences are around the different topics and what that might mean. So when you're presenting this back and answering the question, what are the different topics appearing in fake news? This is something that you can present and talk about the different themes that are coming out of this text and the different things that are being discussed. Welcome to this last lesson of our practical session. In this lesson, we're going to be covering can we create a custom classifier to accurately classify fake news versus factual news in our dataset. So before we jump into this, let's just refresh our memory on our data. So let's run data.head. We can see here we've got our text clean column that's been appropriately tokenized, lemmatized, converted into lowercase, stop words have been removed, so we're ready to move forward in creating our classification model. We want to create our X and Y variables to split into training and test data. We'll start by creating our X. This is going to be our clean text that we're then going to go forward and vectorize and give to our algorithm as its input. Our Y value is just going to be our fake or factual tag. Now let's move on to text vectorization. So we'll create our count vectorizer as we're going to be using the bag of words model to vectorize this text. Once we've initialized the count vectorizer, we can create countVec_fit and use countVec.fitTransform on our X dataset. We then want to create our bag of words as a pandas data frame. So we use pd.dataframe, and we want to convert our count.vet and convert it to array. The column names of our data frame can be obtained by using countvet.getFeatureNamesOut. So this will have successfully vectorized our text, and it's ready to be split into training and test data. To do this, we want to create our xtrain, xtest, ytrain, and ytest. To split up our training data, we'll be using train test split. We want to split our bag of words dataset and our y vector. We also specify the text size to be 0.3, so 30% of the data is going to be going to our test dataset and won't be used for training. We want to start creating our classifier with just a simple logistic regression to see how this performs and use it as a baseline for other models we may want to try. So we create our LR and use the logistic regression function, and then we want to use .fit and reference our xtrain and ytrain. Our logistic regression model has now been created, and we want to use this to predict our test dataset and compare this to our actuals. So let's create ypred LR and then use lr.predict on our x test. We can then use this to compute the accuracy score. So we'll be using the accuracy score function and comparing the accuracy between ypred LR, the predicted labels from our logistic regression model, and comparing this to our actuals in ytest. You can see here we've got some really good accuracy at 96%. Let's dive into this a little bit further using the classification report. We can see here the model has done amazingly well at predicting fake and factual news. This model is perfectly fine on its own, the accuracy seems really good, but out of interest, let's just see what it would look like if we used an SVM, support vector machine. We create our model using the SGD classifier, and then we reference .fit and our xtrain and ytrain. As our model has now been created, let's again run our predictions using this new model. We create our ypred SVM and then use svm.predict on our test dataset. Again, let's have a look at the accuracy of this model and see if it's improved anymore from our logistic regression. So we can see here this model has actually not performed as well as the logistic regression. This is why it's really important to try simple models first before moving to anything more complex. We print out this classification report again, and we can see here that it's done pretty well. The model has worked well, and it's giving us 90% accuracy across the board. However, the logistic regression has seemed to work better. So to answer the question, can we create a classifier that can classify different news as fake or factual? The answer is yes, and it seems to be quite a good problem for these algorithms. They seem to work with really good accuracy. So I hope you've enjoyed working through this practical lesson as we run through each step by step with the same data and see what that process would look like as a full NLP project. You've now got a really good project to put in your portfolio and show off your new NLP skills. Welcome back, and I so hope you've enjoyed working through the different topics on this Introduction to Natural Language Processing course. Of course, the field of NLP is huge, and there's always new things evolving and new things being developed. In this last chapter of the course, we'll be discussing deep learning, its applications, and where we think NLP might be going in the next decade. Before we start discussing how deep learning has impacted the field of NLP, let's first clarify what we mean by deep learning. This is just going to be a high-level introduction.
we're not going to do any code, but if you are interested in creating your own deep learning models, there's a great course on the 365 data platform that I would definitely recommend. So let's get started. Unlike traditional machine learning algorithms, deep learning, also known as neural networks, are built to simulate the human brain and its structure and function. These neural networks consist of interconnected layers that aim to analyze data and uncover patterns. Neural networks consist of input layers, hidden layers, and output layers. Each layer receives its input, applies an activation function, and then passes it on to the next layer. Each layer consists of individual neurons, and the strength of the connections between these neurons, known as weights, determines the impact of these neurons on the final prediction. By adjusting the weights between these neurons through our model training, neural networks can learn from data and use this to improve their performance. There are several different types of deep learning architectures, each suited for different types of tasks and data. For example, convolutional neural networks excel at image and video processing by exploiting spatial correlations. On the other hand, recurrent neural networks use connections that can process feedback loops, so these excel at processing sequential data such as language for NLP. Training a deep learning model involves optimizing these individual weights of the neurons to eventually minimize the difference between the predicted output that our algorithms are giving us and the actual output that we're looking for. Deep learning has made remarkable strides over the past few years and really pushes the boundaries of what we thought would be possible. With the advancements of hardware capabilities, deep learning has become much more complex, able to handle massive amounts of data. It's a super interesting field and especially has amazing implications for natural language processing. So in our next lesson, we're going to be discussing how this relates to NLP and the advancements that have been made in deep learning with NLP over the last few years. So now you have at least a basic understanding of deep learning, let's discuss some of its applications for NLP. One of the most famous examples at the moment, and maybe the reason that you reached out to look for this course, is ChatGPT, an advanced language model built by OpenAI. At its very core, ChatGPT uses a neural network architecture called a transformer. And if you think back to our lesson on sentiment analysis, you'll recall that we use one of these pre-trained transformer models to discover sentiment in our text. More generally, ChatGPT is an example of a large language model. Large language models are designed to understand, process, and create human-like text by learning from a vast amount of data. These large language models are trained on vast amounts of diverse data, from books to websites, articles. Loads of different text data is fed in to allow the understanding of human language, of patterns, semantic relationships, and grammar, so that human-like text can be generated. These models have demonstrated significant advancements in the field of NLP, and have found use cases across the board in chatbots, in content generation, in language translation, so many different applications for these large language models. As we continue to refine and advance these models, the potential for more interactive and more sophisticated advanced human-computer interaction becomes more attainable. So it's a super exciting time to get started in the field of NLP, and I'm so happy that you decided to start your journey with me in this course. As we've been working through the practicals in this course, you may have noticed we often reference the language we want to use. For example, when we were creating our Spacey model, we specified an English language model, and when we're using our stop words, again, we specified we wanted these to be in English. This course has focused on using NLP with English language data, but there are loads of developments being done in other languages that mean NLP solutions can start being used for a global audience. However, it is quite challenging as some languages just don't have the large amounts of easily accessible data required to train these kind of natural language models. Even the way we pre-process text needs to be adapted for each individual language to take into account different grammatical rules and sentence structures and contextual information contained within the written language. So if you're wanting to work with non-English data, what do you do? Well, the first thing I'd recommend is checking out the documentation of the packages we already used and see what kind of languages they support and whether you can just switch out the language models that we used, but continue to use the same code. The other option is to check for additional packages that have been developed with your language in mind. So for example, the NLTK package has been developed for the Indic languages such as Hindi and Tamil. Expanding the language capabilities of NLP is a key aspect of future development to help ensure we create inclusive solutions for a global audience. So, in our next and final lesson, we'll look at some of the advancements of NLP and where we think it might be heading in the future. The field of NLP is expected to continue to evolve rapidly, with technological advancements and the increasing availability of large-scale datasets for training. Here are some ways we can expect NLP to evolve over the next few years. The first is that NLP is expected to gain a deeper contextual understanding, so getting better at understanding semantics and general word knowledge, and even being able to have reasoning capabilities behind its decisions. The second is multimodal understanding. So NLP will be fed not only with text data, but with images, videos, and audio, so that the language model can get an even better understanding of how language works in the different contexts it can be used. As the demand for faster, more interactive NLP solutions increases, we'll also see advancements in the optimization of model architectures, as well as the technologies required to deliver more real-time solutions. We're also going to be hearing more conversations around ethical considerations, biases, and privacy concerns to ensure we keep fairness, inclusivity, and transparency at the forefront of any new NLP development. As you'll have seen going through this course, NLP has so many amazing applications for our everyday lives. I truly hope you've enjoyed going through this course with me, getting an introduction to natural language processing, and hopefully you're ready to start building some NLP solutions of your own.